So thank you very much, Bob, for the invitation to come and speak here. And thank you very much to whoever prepared these amazing badges. I think it's the best name badge I've ever had. So I have no machine learning background, really. I'm a mathematician, a physicist. My background is in climate science, statistics, modelling, nonlinear dynamics. I'm interested in modelling complex systems. So how many of you in the audience know roughly what the word epistemic means? You put your hands up. Okay, a smattering, but not all of you. So I'll define it first then. So epistemology is the philosophical study of knowledge and how we gain confidence in what we think we know, how we understand the world and how we think we understand it. So it's kind of the study of knowledge, if you like. And so what I'm going to talk about is some sort of slightly broader concepts in not just machine learning, but how we understand the process of modelling as a whole, how we expect to model the real world and get the right answers, especially for particularly complex systems. Okay, so I'll start with the Hawkmoth Effect, and then I'll move on to talk for an example that I'm familiar with, which is climate models, and I'm sure you can think of other examples that you're familiar with. I'd encourage you to sort of jump in and ask questions as we go along. I haven't got a huge number of slides, so there's plenty of time. Do ask questions mid-flow. I don't mind that at all. So the Hawkmoth Effect. How many people have heard of the butterfly effect? Almost all of you. Great. Okay, so we'll start with the butterfly effect. If we're making a forecast, if we're using a model to make a forecast or a prediction, then we start with some initial condition. Perhaps we have I'm thinking here probably of a dynamical system that evolves over time. It wouldn't necessarily need to be one like that. It could be a model that is evolving in some other way. And you evolve that forward using your model, and you make a forecast of what you think the outcome will be. Now, the butterfly effect says maybe we can't measure those initial conditions perfectly. Maybe we don't know exactly what our boundary condition for this problem is that we're trying to solve. So, supposing we have some uncertainty there, and we maybe take a number of possible initial conditions that are consistent with our observation, and we evolve all of those forward, then we can make a forecast that is a probability distribution. You know, we can say, all right, we've got this initial condition plus or minus some vector of error, if you like, observational uncertainty. We evolve it forward according to our model, or according to hopefully the real world, and we make a forecast which we can, if we have the perfect model, we can guarantee that that forecast is going to be a good forecast in a probabilistic sense. It won't always get the right answer, but the right answer will always be within that probability distribution, right? So that's the butterfly effect. Small changes here could lead to big changes here, but we're capable of predicting what they are. You know, we have a mathematical, statistical way of getting at that uncertainty and always accounting for it correctly probabilistically. So the Hawkmoth effect. Supposing instead that we don't have a perfect model, we don't know what the underlying dynamics are of the real world. We don't know, we can't define this perfectly. Then we have a model, and we have our initial condition that we observe, again with some error, some uncertainty. And we use our model and we evolve that forward, and we get an answer that's not the same as what we would have got from the real world, the perfect model. So how do we get at the error that we're going to be making in our forecast? How do we understand how bad this might be? What's the divergence between the real world outcome and what we're forecasting? Well, we can go back and we can sort of do the same thing again as we did for the butterfly effect. We can look at our initial condition error, we can make a probability distribution around that, and we can take some sample of that and evolve all of those forward, and we'll get some other probability distribution out the other end. And are we done? No, we're not done, because we still have a probability distribution that potentially is quite different from the real world. So the question is then, how different can the model be from the real world such that this starts to become a problem? Is it the case that actually, if we're only slightly different, slightly wrong physics, but we're kind of getting there, we've included most of the processes that we think are important, we're getting it, sort of, what I'm getting at here is the idea with the horses of getting the right answer for the right reasons. We have a good model, maybe we have a y equals f of x for the world, some function, f, and our model differs from that only in some epsilon term, some very small amount. So we've got y equals f of x plus epsilon of x, and our model is actually, in that sense, a very good model of the physics of the situation, of the dynamics of the situation, of what's actually going on in the real world. Well, what we'd like to be able to do is sort of, again, take a sample around this. Instead of taking a sample around the initial condition, we want to take a sample of alternate possible model structures. Now that's impossible, because the space of all possible models is infinite dimensional. So although the initial conditions may be well defined, and the space of the variables in which that model or the real world exists might be, hopefully, well defined, and we can sample all possible initial conditions given that observational uncertainty, we can never hope in a real world scenario ever to sample the space of all possible models, nor can we hope to sample it, in a sort of independent, identically distributed, sensibly well-distributed fashion. And so we're left with the difficulty that the real world and the model world could diverge. So that's the Hawkmoth effect. Now, there's a mathematical result, and the butterfly effect we can always deal with. We can make that probability stream. We can make a good probability forecast. In the mathematics of complex dynamical systems, there's a result which essentially says that complex systems are not structurally stable. There is no general guarantee in dimensions greater than 2 that any complex system will be structurally stable, i.e. that a small perturbation of the order epsilon to the dynamics, the underlying dynamics of this situation will cause a small change in the outcome. So we can expect in general that a order epsilon perturbation to the dynamics of the situation may well result in an extremely large variation in the outcome of our forecast. Oh, where's it gone? Yeah. So your equations can be arbitrarily close to the correct equations and still get completely the wrong answer. Your trajectories could differ by much more than epsilon, by a large amount. Okay, so what does that have to do with what we're talking about today? I think that this has fundamental consequences for the question of what we mean by a good model, right? If you're getting the right answer for the right reasons, you think you've got a good model. If you're getting the right answer for what you perceive to be the wrong reasons, we're calling it a horse. If you get the wrong answer, but you were using sort of the right reasons, were you just unlucky, or is that a problem that we can't avoid, or what's going on there? If you get the wrong answer for the wrong reasons, let's say it's a dead horse. Hopefully we don't construct too many of those models, but maybe we do. I mean, maybe all models, in a sense, have to be dead horses, and it's only because we're not being sufficiently rigorous about the way that we're thinking about the situation that we would ever classify anything as either a horse or unlucky And maybe good models in this sense are only possible in a mathematically ideal, mathematically perfect situation. So I'd be interested, on your thoughts in when and how that might be the situation. Okay, I'm just going to hope it stays there. So, what do we mean when we say that we are expecting to be getting the right answer for the right reasons? Is it the underlying physics of the situation? Is it the underlying dynamics? What structure are we imposing on that model and on the evaluation of that model when we make those subjective judgments about what we think is a good way to get the answer and what is not a good way to get the answer? I think this has consequences for model development. We start in this kind of, maybe Victorian sort of classical view of science. We start with a bad model, we make it better, we improve it, we go back and we see what it missed out, and we try to start putting in more processes, more assumptions, more complexity, and we think that that will lead us on a sort of monotonic road from a bad model to a better model, maybe eventually to the best model, the underlying model, which is getting the right answer for the right reasons. It's exactly, perfectly matching what the real system is doing. I think that the Hawkmoth Effect shows us that for anything other than the very simplest possible systems, this is simply an unreasonable expectation. It's not fundamentally justified. We could be improving the dynamics of our model. We could be improving what it's doing. We could be making it better in every subjective assessment of what it's doing, but we get a worse answer. So is a model that is sort of passing our tests initially, let's call it a reasonable model, it's sort of getting the right answer but maybe for the wrong reasons. If we then add more complexity, add more processes, make that a better physical model of the underlying situation, maybe we get a worse answer. So do you go from being a horse down to being unlucky? What happens in that situation? I'm kind of throwing out a lot of questions because I don't necessarily have answers to these questions. But I think there's an external perspective on what are the problems in general might be sort of useful context for the rest of this conference. I'm really interested to see the types of situations that you are looking at and contrasting that with my own situation here. So here's an example. Climate models, quite different from what many of you are researching. How would we know if a climate model is giving the right answer? What do we mean by the right answer? We have fundamentally simplified the planet in order to fit it onto a computer. We've picked a number of processes that we're interested in, and we've thrown out a whole load of processes that we know to be important, but which we're not particularly interested in, or we think we sort of cross our fingers and hope may be negligible for the prediction tasks that we're interested in performing. So how do we assess it? I mean, agreement with other models, agreement with past data. We can run our climate models on past weather and climate data and see how well they do in that situation. But it's not out of sample at all. We've used that data to construct the model, so we really have very little independent data on which we can go back and evaluate. So the sorts of reasons that are appealed to as ways of demonstrating the quality of these models and their performance in future prediction tasks is things like whether they agree with each other, whether they agree with our physical intuition about what ought to be happening, given our mental and conceptual models of climate change, how we understand the physical system and the way that we personally or as scientists or as groups of scientists abstract those physical processes into our models, which are not the same as the computer models. Making pretty pictures, if it makes a model that sort of looks plausible, it evolves in a way that we think looks kind of like the real system, But again, we're always in this difficult regime where we don't have much in the way of data to test it on. You might say this is totally irrelevant to me because I've got lots of data and I can always test my model. But I think that while there is a big difference between the if you like, weather-like tasks where you have a lot of data and the climate-like tasks where you don't have a lot of data, in some sense they are performing the same function, and because we are not in a mathematically ideal situation, I think that they have more in common than they have different. And then how do we know that the climate model is giving the right answer for the right reasons? Well, I think we are stuck in a circular argument of saying we think it's giving the right answer because we think it's using the right reasons, and we think that the reasons are right because the answer sort of looks plausible. I don't think that there's any epistemic basis for any... Really, for an out-of-sample test, I think there's never an epistemic basis for any judgment that a model is doing well, apart from a subjective feeling that it looks okay and we sort of believe it. And that's all right. This is what much of modern science is founded on. This is not a problem. The important thing is to be clear about where that's coming from and what that means for the decisions that we might take based on these models. So, the IPCC, that's the Intergovernmental Panel on Climate Change, in their last report, they do effectively, more or less, they don't say it in these words, but they state the probability that climate models are horses, i.e. that they may be getting the right answer for sort of maybe the right reasons on the data that we have so far, but we shouldn't trust them in future. So would anybody like to hazard a guess of what probability they would put on that? Is it of the order of tens of percent, 1%, 0.1%, 0.01%?
1 in 3.
1 in 3. Anyone else?
90.
90%.
Yeah. Did they just get down and say they got the last one wrong? Was the report that they just said the predictions we made 10 years ago were totally wrong?
I don't think they've ever said that.
I thought it was a news story there.
Now, there may well have been a news story, but it's probably not what the IPCC said. Stay away from the Daily Mail if I were you. Numbers. Anyone else? 3%. 3%. So 3%, 90%, 1 in 3, 30%. Anyone else?
5%.
5%. 24%. So 1 in 3 wins the prize. Well done. So why did they make that probability statement? Where did that come from? So they make these projections using climate models, using a large set of climate models, what they think the outcome is going to be for temperature in 2100. They present this as a table for different scenarios of global mean surface temperature change. They get a range from the models, which is a 90% confidence interval from the models, and they then downgrade this in a footnote. I can give you all the references later if you want. But in a footnote they say, okay, we take our 90% confidence interval of what the models do, and we're going to downgrade that to a likely range, by which we mean 66% probability. So 90 minus 66 is 24. We take our 90% confidence interval of models, and we call that a 66% chance that the real world outcome will be within that range. So rephrasing that in the terms of this conference, I would say that kind of matches up. I mean, you can argue about terminology, all right, but essentially a 24% chance, order of magnitude, that these models are getting the right answer on present-day data for the wrong reasons, and our confidence in what they might be doing in future could be misplaced, and that the actual probability of the outcome being within that range is smaller, therefore the probability of it being outside that range is larger. They don't say anything about whether that probability is on the upward side or the downward side of projections. I mean, personally, I tend to think that it is likely that we are less well understanding the things that are further from our present experience, and therefore that more of that probability is on the bad side, the increased warming, the more extreme climate change. But you can find people who will argue that it's symmetrical. I haven't found anyone who argues that it is skewed towards the good side, apart from implicitly in remarks that people like Nigel Lawson make. But no scientists. So, coming back to a wider question then, are all models horses? I think, how do we know that all scientific models are not horses? Out of sample testing. So obviously that's what you try to do a lot of. You can, if you do enough out of sample testing, then you can be confident that for the conditions you have surveyed, you don't have a horse. But, what about all the other conditions that you haven't thought of? Is it a horse in some other respect? If you're in a really nice, well-constrained, mathematically ideal situation, you can be confident. But if you're in the real world, you probably can't be confident. Does that matter? If you have a model, and you test it out of sample and it works, does it matter if it's a horse anyway? Do we mind a bit of equine DNA in the beef burger? Do we really care? So there are interesting discussions in the climate community, in other physical modelling communities, about the role of statistical models versus dynamical models. How we should, because the statistical models are more or less a black box. They're the sorts of things that you're working on. They are the things that, you put in your inputs and you have some kind of structure and you generate outputs, but that structure is not necessarily related in any way to what we think of the underlying physics of the real world situation. And dynamical models, we sort of feel, anyone who's grown up as a physicist will feel that they have fundamentally more confidence in the ability of a dynamical model, something which is based on the real physics of the situation, to make better predictions out of sample than a statistical model which has only been trained on the data that we have, on the basis that the laws of physics hopefully are going to be the same in the future as they have been in the past. I think that's not an unreasonable assumption. If you don't make that assumption, what are you going to do? All right, we might be stuck if we don't. So I suppose my challenge to you is, why do you care if you have a horse? Are we surrounded by horses, and actually we shouldn't mind? Perhaps even as a horse, they're still abstracting something which is informative and is useful for the real world. And ultimately, is that not the test of our capabilities, being able to do something which is useful for the real world? If models can't be tested out of sample, how do you know that they're not horses? Well, you can't know, you're just stuck. You can't know, you can never know. In some sense, they must be horses. They must all be horses, because they are always prone to the Hawkmoth Effect. Every dynamical system that we study in more than 2 dimensions, which is everything, will be prone to this Hawkmoth Effect and therefore can never be using the right reasons. We can never have a perfect model of the real world. But then that's the whole point of doing modelling, is to make these abstractions and to say, okay, we don't need another copy of the real world because we don't understand the real world anyway. That's why we're making a model. So the model is wrong. All models are wrong by definition. That's why we're making a model. We want something that's wrong because we want to be able to understand it. So I think, that square, the right answer for the right reasons, really is empty unless you're a pure mathematician. But that doesn't mean that we are stuck without any science. We can still make useful expert judgments about the quality of predictions that are made by the models, even if they're horses. You are still forced to bet on the probability of one of your horses winning. They're there, they're lined up, they're going to run. What are you going to do? What decisions are you going to make based on the output of these models? Having a horse may still be better than attempting to run by yourself.